Hello guys, good evening. Hi YouTubers, good evening. So I'm waiting for students to arrive. So we will be starting our class today exactly by 5 p.m. Hope everyone is able to hear my voice. Yes. Hi guys. Hi Krish. Hi Pushwant Nayak. Hi. So what's up guys? So hope my voice is clear to you guys first. I mean, yep. So today in our today's class, we'll be going to study about electrostatic potential. So we'll be learning about potential energy. So so first we'll recall our basics of gravitational potential energy, whatever we learned in our 11th. Then we'll be talking about potential energy and also about electrostatic potential, electric fields. Um, the electric potential and potential difference today. So we'll be talking about all these, discussing about all these concepts today, and we'll be solving few conceptual questions. And once we are done, we could go on for other problem solving. So guys, I hope all of you try to solve your DPP, which I shared with you guys in your notes. Guys, please reply if you have got access to your notes drive, YouTube. The people from Shillong and Hyderabad region, Shillong, Hyderabad, and Pune region, please reply in your chat box at YouTube. So if you have received the notes and also the physics DPP in the notes folder. So I had shared the notes folder to you guys, right? So I see some 2 3 people, 5 people plus are available in YouTube. Please reply. Well guys, hi. So we'll wait for our students to arrive in Zoom, as well as please inform all your classmates so that they could arrive to the class. So inform all your friends, classmates to attend the class. So today's class, I hope it would be interesting for you guys. So we'll be learning about electric potential and electric potential energy. We'll derive an expression for that and we'll continue. So in previous class, guys, in previous class, there was a doubt on this particular question. The doubt was, yes, sir, what was the electric field of an isolated metallic sphere at an interior? Or actually, it was not the question. Actually, this was the question, the third question. So we were discussing the answer solution for this question. If a conducting medium is placed between two charged bodies, then yes, if a conducting medium is placed between two charged bodies, then the electric force between them will become what? What is the electric force between them? What's the question, guys? So that was the question which was asked. So it was 0. So someone asked me the doubt, sir, why is it 0? Why is it 0? Okay. So we'll discuss about this today. I think I had mentioned about that in the notes, the third answer. Explanation, I had mentioned it in your notes. If you have missed it, please check your notes once again. Okay, I'm waiting for students to arrive here. Hello, good evening, Shilpa. Hi. So hope you guys hope you are doing great. Hi Shilpa, good evening, and please inform all other students to log in. Hope all students are aware of this. Yes, good evening Shilpa. ಸೊ ಹೇಗಿದ್ದೀರಾ? ಏನು ಸಮಾಚಾರ? ಎಲ್ಲಿ ಯಾರು ಕಾಣಂಗಿಲ್ಲ. Yes, guys, hi, good evening, guys. So we'll start our class exactly by 5 p.m. So hello guys, hi, good evening. Hi Dikshita, hi Tejas, good evening. ಸೊ ದೀಕ್ಷಿತಾ ನೋಡಿ, ಅದು ಕ್ಲಾಸಲ್ಲಿ ತುಂಬ ಕಡಿಮೆ ಜನ ಇದ್ದಾರೆ. ಲೈಕ್ ಏನಾಗಿದೆ ಸ್ವಲ್ಪ ಕ್ಲಾಸಸ್, ಟ್ರೈ ಟು ಇನ್ಫಾರ್ಮ್ ಇನ್ ಗ್ರೂಪ್. ಸೊ ಹಾಯ್ ತೇಜಸ್, ಹಾಯ್ ಪ್ರಕಾಶ್. Okay, cool. Hi. Good evening, guys. Hope everyone are doing great. So, guys, I hope everyone have tried your problems. Like, yeah, hi, Prakash. So, everyone tried to solve your DPP, I guess. Everyone have tried. So, guys, quickly take your technical check if I'm audible and if my screen is visible. Please give me confirmation if my voice is clear to you, clear and loud and clear to you, and my screen is visible to you. Yes, please give a confirmation, leave a confirmation message for if you are able to hear my voice clearly and if you are able to see the blackboard clearly. So, yes, please take your polls, guys. Okay, little louder. Okay, so I hope now it should be fine. Dikshita, hope I'm loud enough for the class. If not, please let me know, okay? Yes, thank you. So we'll start our class with a small discussion about yesterday's doubt. So we had a doubt from one of the students from YouTube or from Zoom. I don't remember. So the doubt was about the third question. The third question here says, so we had taken the recall test already. So in the third question says, if a conducting medium is placed between two charges. So if we have two charged bodies or two charges, then the electric force between them. So if we keep, say, I have two charges, so I have two charged bodies, say I have two charges, and some, yeah, I won't give them name. I'll give them two charges. Say I have two charges, Q and Q, or Q bar or whatever. So if I place a conducting medium between them, if I place a conducting medium between them, so what happens to the electric force between them? So what happens to the electric force? What is Fe? Come on, guys, reply in the chat box. What happens? So the answer was zero, but how? Answer was zero, yes, but how? How? Why? Why is answer zero? Please answer this question. So why? Hope I guess most of you got this question, sir. Yes. So when we keep a conducting medium between two charges, the electric force between them will be zero. Why? Come on, guys, tell me. Try to answer. Try to guess. Come on. You guys have to guess. At least guess. Not at least guess. You have to guess. So what could be the possible reason? So I have two positive charges. Say if there exist two positive charges in free space, they exhibit which type of force? Yeah, there exhibits repulsion between them, right? Now, in between them, if I keep a conducting medium, all of a sudden my force vanishes. There is no force at all. Force ko tata, bye bye, gayab, maya. What happened to that force? Why did the force vanish, or why is the force magnitude of force is zero when I keep a conducting medium? So this question is very very important for you guys to ask. I mean, for you guys to answer. So why do you think? So why do you think there is like the force is zero? Why do you think the force becomes zero when there is when we keep a conducting medium? Yes, guys, come on. Yes, correct, correct, Krish. I'll call you Krish. Okay, correct, Krish, from the YouTuber. Thank you. So yeah, your answer is correct. Yes. So what permittivity? So guys, we know what is the formula for. Yeah, we'll quickly solve this. We know the formula for electrostatic force. The formula for electrostatic force Fe is 1 by 4 pi epsilon naught or epsilon into q1 q2 by r square. What about this epsilon, guys? What about this epsilon? What is this epsilon? What is this epsilon? What is this epsilon? This epsilon is nothing but it's called as permittivity. What is permittivity? Yesterday we learned permittivity. Okay. Or no, in our yes, correct, Amit. So epsilon is permittivity. But what do you mean by permittivity? Yes, correct, Dikshita. It's kind of opposition. It's kind of opposition, or it's kind of more like the term which you are familiar by now is resistance. Yes, it's kind of opposing. It's not opposing force. Yes. Yes, correct, Hari Prasad. Yes, yeah, that thing is going to happen. Yes, exactly. Yes, correct, Prakash. So permittivity means, yes, yes, Devika Rani, correct. So permittivity means how much it would oppose an element, or how much it would oppose a charge to pass through it. Say if I have a charge, how much this element or this material would oppose the allowing of flow of charge through it is called as permittivity. Now, what is permittivity in general, guys? Permittivity is not only epsilon naught. So what is this? Epsilon naught. What is epsilon naught and what is only epsilon? Is there any difference between epsilon and epsilon naught? Yes, Pranay, cool. Yes, correct. So what is the difference between epsilon? Is there any difference between epsilon naught and epsilon, guys? Is there any difference between epsilon naught and epsilon? Yes, what is that? What is epsilon naught? What is epsilon naught first? What is epsilon naught? What is epsilon naught? Yes, epsilon naught is absolute permittivity. Yes, epsilon naught is absolute permittivity. What does that mean? It means it's a permittivity in free space only. It's a permittivity in it's the permittivity of object in free space only. Free space or air only. Right? Now what is epsilon? Correct, Krish. Awesome. You are awesome. So epsilon is nothing but its combination of epsilon naught it's the product of epsilon naught into epsilon r. We had discussed this, guys, in our when we introduced epsilon naught, or when we introduced permittivity. I had discussed you, had taught you this, that epsilon is, yes, epsilon is nothing but epsilon naught into epsilon r, where epsilon r is called as what? What is epsilon r? It's the relative permittivity. It's the relative permittivity. Right? So what is relative permittivity, guys? Epsilon r is equals to, say, if my conducting medium has a permittivity of k, then say the permittivity of my material with respect to absolute permittivity is my relative permittivity, which this we had discussed earlier. Remember, guys, when we started with permittivity concept, we had discussed this. Relative permittivity is nothing but the ratio of permittivity of material with the permittivity of free space. Okay, this was relative permittivity. Now, the relative permittivity of a conducting medium, the relative permittivity of a conducting medium is infinite. Why? As Hari Prasad had, yeah, I think Hari Prasad had given that answer. Why? So, so if you remember, inside an electric conductor, say inside a conductor, say what happens inside a conductor when we bring a charge. Say if we bring a positive charge near the conductor, what happens? If this is a positive charge, when we bring it near the conductor, what happens? Come on, guys, tell me what happens when we bring a positive charge near a conductor. Yes, redistribution of charges takes place, making making. So what happens? There exists an internal. So because of this external electric field, there exists an internal electric field, and hence nullifying. At one point, the internal electric field and external electric field will be equal, and hence inside a conductor, my net electric field inside a conductor is zero always. So by this concept, I can say the charge, this charge is not at all allowed inside the conductor. By this concept, yes, correct, Devikarani. By this concept, we can say my conductor does not allow this charge at all. This conductor does not allow this charge to pass through it at all. It may change. It may what's happening here? It may induce some charge, but it's not allowing this charge to pass through it. So, what can we say about its permittivity, relative permittivity? What can we say about its relative permittivity? The relative permittivity of conductor is infinite. Okay. By this, we can conclude the relative permittivity of my conductor is infinite. If my permittivity is infinite, what happens if I plug in the value of epsilon naught in Fe? So that will become 1 by, so Q1, Q2 by R square into 4 pi of infinity. So there exists a term 1 by infinity. Now what will this term become? The force. What happens to the force? Reply in chat, guys. What happens to the force? Yes? Come on, guys, tell me what happens to the force. The force experienced between the charges will be 0. Okay, this was the explanation for this question. I tried to give that in also in your notes yesterday. I had mentioned here the third answer for you guys. So this is how the conductivity, or when we keep a conductor between two charges, the force between the two charges becomes infinite. So this is the explanation which I gave, and hope all of you have understood this. Yes? Click on us if you have understood this. Guys, please reply. Got to know why my conductor has infinite relative permittivity, right? Why my conductor has relative permittivity equals to infinity. I hope you guys have got to know that by now. Yes, guys, cool. So we'll move on. So in today's class, yes, correct, Surendra, correct, Vargava. Awesome, awesome. Yes. Okay, guys. So in today's class, we'll start with a new concept today. So we are going to start with the potential energy. So we'll be starting with electrostatic potential energy. So we'll be starting with electrostatic potential energy. But before that, let us recall some concepts of gravitational potential energy. So guys, come on, tell me what is. So I have a series of questions for you. Now, very first question is, what is potential? Come on, guys. I want everyone to answer. What is potential? What do you mean by potential? So what is potential? What is potential? This is my very first question, guys. Come on, tell me. Yes. Okay, cool, cool, awesome. Hari Prasad, cool. Okay, cool. Okay, nice, nice guys. It's super Nitya. Awesome. So the potential, the word potential means it's the capacity to do something. Say the word potential is in general means the capacity to do something. So if I have potential, I can do some work. If I am potential enough to do something, then I am yeah, that shows my potential. So if I'm potential to, if I have enough energy to lift this object, then I have a potential to lift this object. So that is the capacity to do something is called as potential. Now, what is potential energy? So this is to be specific, this is with respect to gravity. So this is with respect to gravity. What is gravitational potential energy, or what is potential energy in general? Yes, Pooja. Cool. What is potential energy, guys? Have we studied potential energy in our 11th? We studied, right? So what is potential energy? Yes, correct. Yes, guys, superb. So energy, it's not produced, Pooja, it is possessed. It's not produced, it is possessed. It is gained. Energy gained. Okay. So potential energy, we can say that the potential energy is nothing but it's the energy possessed or gained by a body because of its position. So because of its position with respect to ground, if a body gains some energy, then that energy is called as the potential energy. Correct, Samrat? It's the energy stored in a body, which is stationary, not moving. For moving, it is kinetic energy, okay? Yes, remember, for moving objects, it's always kinetic energy. For stationary objects, which is, yes, correct, correct, Surendra. It is potential energy. Now, what's happening here? So, suppose if this is considered to be the Earth's surface, suppose this is Earth's surface. Okay, I'm in Earth's surface now. Now, I have a mass. I have a mass of m kgs. I have a mass of m kgs. Now, now, what do you think its potential is? Guys, if I have a mass of m kg, what do you think its potential is? Or what is its potential energy? What is the potential energy associated with the mass of m kgs? Okay, correct. Okay, to an extent, right, Bhargav. Correct, Pranav. So, yeah, guys, come on, tell me now. So, when my body is at Earth's surface, which is on the ground, say simply when my body is on the ground, when my mass is on ground. So, what is the potential energy it gains? What is the potential energy it gains? So, what is the expression for potential energy, guys? Yes, correct, Bhargava. What is the expression for potential energy? We know. What is the expression for potential energy? So, guys, correct, Devika. Correct, Devika. So, yes, correct, Dhanush. It is m into g into h. So, potential energy in general is given by m into g into h, where m is mass, g is acceleration due to gravity, then h is h. What is h? What is h, guys? H is any height. Now what is happening here? When my mass is touching on, is on the ground, when my mass is on the ground, what is my h? H will be equals to 0, right? So when my mass is touching the ground, my potential energy is 0. The potential energy is minimum, or my potential energy is 0. Okay. Now what I would do, so I have to shift this mass from this position to this position. I have to shift this mass from here to here. What I should do? What should I do? To shift this mass from ground to a height h, what should I do? Come on guys, tell me answer. Yes, we should do work. What type of work? So what should we do? We should put some amount of force. Yes, we should apply some amount of force to lift this mass. So yes, correct. We are going to do some amount of work. We are going to do some amount of work in lifting. So we are going to do some amount of work in lifting this. So we are going to apply some force against the gravity, right? Yes, correct, Sahana. Oh, sorry, Samrat. So we are going to apply some force to lift this. Okay. Now, what happens to this force which is being used? So this force, correct, Krish. So we'll be applying some force to this body which is here. Now we'll be applying some force and we keep this body at this position. Now what happened to this force? What happened to this force? Yes, against the gravity, yes, correct. We lift this object of mass m kgs against the gravitational force and we keep it at height h. Now, where did this force go? So we had done some work, right? So this force should go somewhere else. Where did this go according to second law? So we know our force is conservative. Our force is conservative, right? Force is conservative. Gravitational force at least is conservative. So we had applied some force which should be stored somewhere, right? Yes. That force which we apply is stored in this mass as potential energy. Okay, that force was stored in this mass as potential energy. Okay, sir. Sir, why are we learning this now? Why are we reading this? Why do we want this? So we are going to relate this, which we had already learned about the gravitational potential energy with the electric potential energy today. So the potential energy for any mass is given by m into g into h. So whatever the force I applied is stored as energy in this. So when I allow this body to fall freely, what happens? All my potential energy is converted to kinetic energy, and when it reaches the ground, my potential energy would be zero again, right? So this is what we had to learn from, we had to recall from potential energy of 11th standard, the gravitational potential energy. So come on guys, in today's class, we'll be starting with electric potential. Okay. So what is electric potential? Or what is electrostatic potential energy, or what is electric potential energy? So to learn that, we have to consider two charged bodies. Say we have to consider two charged bodies, Q1 and Q2. So consider two charged bodies, Q1 and Q2. Now, what are these charged bodies are? These charged bodies are like charged bodies. What happens in this case, guys? So when we have two charged bodies, which are like charged bodies, what are like charges? Either both positive or both negative, right? So when we have such bodies, what happens? Yes, correct, Danush. So there exists a repulsive force, right? There exists a repulsive force. Now I don't want these two bodies to escape, so what I do, I'll tie a string to these bodies. I'll tie a string to these bodies. See, these two bodies, these two charged bodies would like always to repel each other and try to move away from each other. So what I did, I just tied a knot to these two. So I just tied this and I just tied this and tied a knot to these two so that they don't go farther. So I kept them at a separation of r. I kept them at the distance, at a separation distance of r. Okay, right? Now what do we do? So what do you think the force experienced between them? The force experienced between them is given by the electrostatic force. The Coulomb's law gives the electrostatic force, right? With what force they are repulsing each other? With Coulomb's law force, the electrostatic force, that is K into Q1 Q2 by R square newtons. Now there exists a repulsive force between the two charges, and this repulsive force is in the direction of line joining them. See, these two forces are acting in these directions only. Okay, guys. So I hope this much is understood to you guys. So to learn this electrostatic potential energy, we are considering two systems, Q1 and two charged bodies, actually two charged particles, Q1 and Q2. Both are like charges, so they like to repel each other with the magnitude of Fe is equals to K Q1 Q2 by R square. Now I have tied these two with a string. I have tied these two with a string. Next, what happens? So now what I'll do, acha, I'll tie them. So one of them is trying to escape. What I'm going to do, I'm going to fix one of the charge at one point. Acha, you both are not roaming here and there. So both the charges, you should stay at one point. So what I'll do, I'll bring charge Q1 and fix it at Q. Okay. I'll fix it at origin, sorry. I'll fix this Q at origin. What is my origin? 0, 0. I'll fix this Q1. I'll fix the charge Q1 at origin. Now, what I'll do with the second one? What should I do with the second one? Guys, reply. Tell me, what should I do with the second one? Waiting for the reply. So now if we fix the charge particle Q1, yes, I'll keep the charge Q2 at the separation of R from Q1. So see, I had tied a knot, right? I had tied a knot to these two guys. So you guys are not going to escape. Say you both are like, what? Brothers, you should not leave each other. So you will be tied together. So I tied a friendship band to you guys. So I tied a knot like this. Now what happens? These two are still, they don't want to come closer to each other. So they are staying away at a separation of R only. Now, acha, both are not willing to, yes, both are not willing to stay together. So what I'll do, I'll just cut their knot. I'll just cut this knot here. Acha. So then I'll cut the knot. Yes, I will come there. We'll come there, Hari Prasad. We'll come to that. So let me finish this. So what's happening? So yeah, now these two don't want to stay together. So what I'll do, I'll just cut this string. So the charge Q2, what happens to this charge Q2 when I cut the string? The charge Q2 experiences the electrostatic force and moves towards infinity. See, the charge Q2 just escaped. So it was here. When I cut the string, it escaped and moves towards infinity. Acha, now what should I do? Acha, they went so far. Oh my God. My charge Q2 went so far up to infinity. Now I should bring back these two. These two should not be separated. So what should I do? Yes, correct, Samrat. Yeah. So what I'll do, I have to bring them back from infinity. So these two are experiencing a force Fe, the electrostatic force, that is K times Q1 Q2 by R square. Now, how much force should I apply? So yes, guys, you guys told me I have to bring them back. So to bring them back, I should do some external work, right? So one has one has become angry and went towards infinity. Now I have to convince him and bring him back. Now to bring him back, I should do some work. Now to do work, I should apply some force. How much force should I apply? How much force should I apply? So to bring them back, I should apply some force, right? How much force should I apply and in what direction? Reply, guys, come on, reply. Yes. So how much, I hope you have understood, you got my question. So what's happening? The charge Q2 became angry with Q1 and left towards infinity, right? Now, you guys told me I should bring them back to the separation where they were initially. So to bring them back, I should do some work, right? To do that work, I should apply some force. What is the amount of force I should apply? Yes, correct, Tejas. So we should apply the same amount of force in the opposite direction. Correct, Dhanush? Cool. So, yeah, we should apply the force. Yeah, what should we do? You guys told me already. We should apply the force in the opposite direction. The force magnitude is same as that of the force which they went. What does this signify? What does this signify? So we have to push this charged particle Q2 in the opposite direction. For this to happen, some external force or external work is to be done. Okay. Yes, correct, Bhargav. So this external work which is to be done is equal to the electrostatic force which it experiences already, and this is to be applied in the opposite direction. Now say I'm applying this force, what happens? So this Q2 moves back near this position. The external force applied is given by, so this external force is which is applied is given by, correct Samrat, cool, superb. It is minus of k times q1 q2 by r square, or that is minus of q1 q2 by 4 pi epsilon naught into r square. Now what happens? So what do we get from this? What do we get from this? So guys, this conclusion, this thing is very important. This ensures, so if we are applying some amount of force, I mean if it's experiencing some amount of force to go towards infinity, now if we are allowed to apply the same amount of force to bring it back, this ensures us one thing. What does this ensure? This ensures us that Q2 is not getting accelerated at any time. Q2 is not getting accelerated. There is no external force acting on Q2, so it's not getting accelerated. So, or we can say there is no external kinetic energy acting on Q2. See, Dhanush, yes, that's what I was meaning, Dhanush. Dhanush, yes. Dhanush, I hope I answered your question. The same force is applied. See, I told my force is conservative. My force is conservative, right? My force is, since my force is conservative, and there is no external force acting on Q2, Dhanush. There is no any other force acting on Q2 other than Fe. See, when this was here, yeah, when this was here, there was only FEB which was being acted, and when we are trying to bring back, we are applying the same amount of Fe to this to bring back, because there is no any external force acting on it. So the Q2 is not accelerating. Q2 is not accelerating. We are applying the same amount of force. Okay, got it? So this is the very important point to note. Please make a note of this. This ensures Q2 is not getting any acceleration, and hence there is no change in kinetic energy. Okay, got this? Dhanush, please reply if you have got this. Yes, others also. Yes, correct, Samrat. We have to bring it very slowly. Yes. Now, so since I'm applying some force from infinity to bring this charge Q2 from infinity to a separation of R1. So we are doing some work. Now guys, what is the expression for work done? What is work done? Expression for work done. We had studied in 11th. Work done is nothing but, what is expression for work done, guys? It's force into displacement. Correct, Dhanush. Correct, Prakash. Correct, Tejas. It's force into displacement, right? So now I'm going to displace this Q from infinity, from this infinity point till a separation of R or R2. I can say, if I consider this distance as from origin till infinity to this, if I consider this distance from origin till infinity as R1, if I consider this distance from origin till infinity as R1, then the amount of work I do to bring back from infinity to this point where it was initially, if I consider that as R2, then my net displacement is R1 minus R2. Okay, so that amount of force, the Fe, times this displacement, see this much, this amount of displacement is being done, this amount of work is being done on Q2 to bring back. Now we have to derive an expression for this. Now when Q2 is moved from R1 to R2, the external work is done, the external work which is done is given by W external is equals to, yeah, Now we have to derive an expression for work done. Guys, please listen very carefully. Now we are going to derive an expression for work done. So the total work done, I can't add, I can't find the work done for each and every instance. So what I'll do, I'll use the mathematical calculus one, the calculus function, like the integration. Yes. Yes, correct, Hari Prasad, correct, Bhargav, correct, Pooja. So we are going to derive an expression for work done. So we are going to derive an expression for work done. In this expression, what we do, so the work done, the external work done, we are doing some external work, right? Who is doing the work? We are going to do the work to bring this unit positive charge, or bring this charge Q2 from infinity to a separation of R2. So from where to where are we doing the work? We are doing the work from R1 till R2. How much force are we applying? We are applying external force F external, that is equals to minus of Fe in negative Fe direction. In, yeah, this is what we are going to derive. So guys, try to integrate this function. W external is equals to integral of R1 to R2 F external. What is F external, guys? What should I substitute in F external? What should I substitute in F external? Guys, what is W external? Try to solve this. Try to reply, guys. R1 to R2. What is F external? What is my F external? So that is nothing but my Fe. Yes, correct, Dikshita. Correct, Danush. Fe is equals to K Q1 Q2 by R square. Now, note that I'm applying force in the opposite direction. So this Fe should be negative. So whatever the F external I'm applying, this is negative of Fe, that is minus of Q1 Q2 divided by 4 pi epsilon naught R square. So where R is any arbitrary distance between the charge Q1 and Q2. Okay. Yes, guys. Now, what are the things which I could remove out of the integration? So if this is the one, so yes, correct, Hari Prasad. Cool, awesome you are. So the work done external, the external work done is given as this integral of R1 to R2 minus Q1 Q2 by 4 pi epsilon naught R square dr. So we are going to integrate this function with respect to only the variable dr. So rest everything except r, except the variable r, I'm going to remove everything out of the integration. So guys, try to do this, try to solve, try to do the integration part. So I want everyone of you to solve this. Come on, try to do this integration part. See, I'll show you how to do this. So W external is equals to minus of, yes, correct, minus of, yep. W external is equals to minus of Q1 Q2 divided by 4 pi epsilon naught. I'll take this out of the integration. Then integral of R1 to R2 1 by R square dr. Okay guys, now come on, tell me. Yes, correct, Tejas. So what is integral of 1 by x power n dx? So guys, to solve this, you have to know what is integral of x power n. What is integral of x power n? So those who don't know, those who did not take maths as your course, please listen carefully. Integral of x power n is x power n plus 1 by n plus 1. Okay. Okay. I have some n1 to n2. So if this is the thing, then n1 to n2. So this is my integration for integral of x power n. Okay. Now suppose if they don't give you the limits, you have to add plus c. Okay. I hope that you guys know. Now guys, say if we here we have n1 to n2, say here we have x1 by x power n. So this can be written as, okay, dx. This can be written as integral of x power minus n. So dx. What would I get here? Yes, correct, Adi Prasad. Cool. So that is x power minus n plus 1 by minus n plus 1 at n1 to n2. So guys, using these two rules, try to integrate this. Come on guys, try to integrate this with using these two rules. Try to integrate here for expression for work external. Let me know if you have done. Click on S if you have done. Click on S if you have done. Yes. Cool guys. Okay, shall I continue? Okay. So the external work done is given by, yes, correct Hari Prasad. Cool, awesome. Yes, is given by W external is equals to minus of Q1 Q2 by 4 pi epsilon naught into, so I'm going to integrate this 1 by r square is r power minus 2, that is r power minus 2 plus 1 by minus 2 plus 1 from R1 to R2. So guys, if you try to solve this, what you get? W external is equals to minus of Q1 Q2 by 4 pi epsilon naught into R power minus 1 by minus 1. So guys, if you see, this negative term and this negative term would cancel now. This negative term and this negative term will cancel now. Okay. Next, we have the final result. Okay, I hope you guys have understood this. So yes, I'm going to erase this. Any doubts in the integration steps, guys? Any doubts in the integration steps? If anyone have any doubts in the integration step, please let me know. So okay, cool. Then the final expression for work external is given by W external is equals to Q1 Q2 by 4 pi epsilon naught into 1 by R, where my R1 to R2, it varies from, my limits varies from R1 to R2. Now, what is the expression for external work done? Now the external work done is given by W external is equals to, after substituting all the limits, I get W external is equals to Q1 Q2 by 4 pi epsilon naught into 1 by R2 minus 1 by R1. This is my expression for external work done. Guys, how many of you have got this? Click on S. How many of you got this? Click on S. Come on guys, come on. Click on S. How many of you got this? Yes, good guys. Very good. So if you got this, it's very good. Okay. Now, okay, what can you conclude from this? So there's an interesting property here. Now, say what was happening here. So I had my charge Q1, which was fixed here at origin, fixed at point O at origin. Now I had to bring this, I had R2 here, the separation between my Q1 and Q2. So this is my Q1. Okay. Now I had to bring this Q2 from infinity to a separation of R2, right? Now there is an interesting property. What do you think that interesting property is? So guys, get any guesses? Any guesses? What do you think would happen? What do you think would happen? So we said our charge, our force Fe is conservative in nature. Our electrostatic force is conservative in nature. What does conservative in nature means? What does conservative in nature means? So it means the external work done to move this charge, depends only on initial and final positions only. Yes, it depends only on initial and final positions only. but not on path, but not on path. So if I want to bring this unit positive charge, or if I want to bring this Q2 from infinity to this separation of R1, I can bring it straight, I can bring it like this, or I can bring it like this. In all conditions, my work external is always equal to this. In all conditions, my external work done is always equal to this magnitude only. So this expression signifies as my external work done only depends on the initial and the final positions only. Okay, it depends only on the initial and final positions only. Okay, so this is the property. The work done in moving the charge Q2 from R1 to R2 is independent of the path taken, because the force which we are applying is conservative in nature, hence it depends only on initial and final positions only. Okay. Okay, guys. Yes. So I have a quick concept test. Hope everyone have understood how we derived external force, I mean external work done, expression for external work done, and also the concept behind the conservative force, and also the work done. Guys, so I hope all of you have understood till here. Please click on yes if you have understood till here. Is there any doubts, guys? Is there any doubts anywhere at any point? Is there any doubts at anywhere, any point? Achha, someone has a doubt. Okay, no doubt. Okay, cool. Okay, if so, then try to answer this question. Try to answer this question. The electrostatic potential. Oh. Try to answer this question. Yes. Electrostatic potential energy due to a point charge is the work done by dash in bringing the charge from infinity to any other position R. So who is doing the work? The question is, who is doing the work? Who is doing the work? So electrostatic potential energy due to a point charge is the work done by whom? The electric field, an external agent, neither of them, or both electric field and external agent. Who is this? So in this case, we studied for two like charges. Okay, thank you, Pranay. Thank you for the confirmation. Yes. So in this case, we studied for two conditions. Okay, I mean only the like charge conditions. Say if we had like charge and unlike charge, it depends. So let us answer only for two positive charges. Here they have mentioned in the question also the point charge plus q and plus small q only. Okay, Hari Prasad, what is that? So W external is equals to 2F by R. Yes, I think I have to check that. So your question is if R1 is equals to R2. So when R1 is equals to R2, I don't have to do any external work done, right? So it's still in the same, it's still in the same position. Yes, Dhanush, Audu. Correct. For unlike also work should be done and it's same as the external work done. Okay. For unlike charges also, when we are doing work, it's always positive and external work is to be done. Yes, guys. So I'm going to end the vote, guys. I'm going to end the poll. And yes, the correct answer is option B. Yes, the correct answer is option B, an external agent. So always an external agent is required to bring the positive charge or test charge from infinity to the position R. Okay. Okay, guys, if you have done that, please try to solve this. So I have a question again for you guys. Yes. So a work of 100 joules is performed in carrying a charge of minus 5 coulombs. So this is exactly what Dhanush had asked, right? I think, yeah. So a work of 100 joule is performed in carrying a charge of minus 5 coulomb from infinity to a particular point in an electrostatic field. The potential of this point is option A 100 volts, option B 5 volts, option C minus 20 volts, option D plus 20 volts. So note this, the work is done by external agent always. Work is done by external agent only. So guys, note this, the work is done by external agent only. I'm stressing on this. Yes, Krish, correct. Prakash Kora check, Dhanush check, Krish correct. Yes guys, come on. So this is kind of a tricky question for you guys, correct Prakash? This is kind of a tricky question for you guys because you are very easily tricked. Only students who get, I mean, yeah, this is a bit tricky question. Dikshita check, Tejas correct, Nitya check. I'm waiting for everyone to answer. Yes, correct Adarsh. Yes, correct Dikshita. Yes. Radhika correct. Pooja correct. Awesome guys. So I have got correct responses, most of it, and I'm going to end this chat. I mean, end this poll. Okay, I'm going to end this poll. Cool. So most of you see, as I mentioned, most of you got tricked with option C. Most of you got tricked here. Okay, correct answer is option D. Okay, I'll just disclose this. The correct answer is option D. Why? Sir, we know what is given. What is given to us? What is given to us, guys? Given work done. Work done. Yes, 100 joules. Now, who is doing the work? And what is the charge? Charge is minus 5 coulomb. From distances, R1 is infinity and R2 is some point. Okay, from infinity to some point R. Okay, it doesn't matter. Now, what is the potential energy? The potential of this point is. So, okay, I had to ask this question after potential. Okay, let's check. So we'll learn this, we'll discuss this question after discussing potential energy. Okay, guys, there is some, did we study? Okay, so this question was supposed to come after potential energy, sorry. So we'll discuss that question again after potential, electric potential. Okay, so let's begin with electrostatic potential energy. So I can discuss there. So you'll be studying in next few minutes. We'll be discussing something called as VV minus VA is equals to W external by Q. Okay, to answer this question, we'll be studying in next few concepts. We'll be studying VV minus VA is equals to W external by Q, or V is equals to W external by Q. So when we are applying, so guys, note one thing, when work is done by an external agent, when we are doing work on the system, it's always positive. Okay, irrespective of whatever the charge is, when we are doing work, it's always positive. That is, work done is 100 by charge is 5. So it is plus 20 always. Okay, so we'll learn this in next few concepts, then we'll discuss this question again. Okay, if not this question, we'll discuss a similar question again. Okay, sorry for this, and yeah, we'll start with the next concept. So what is electrostatic potential energy, guys? By now You might have learned what is electrostatic work done. Now we'll learn about electrostatic potential energy. Now, what is electrostatic potential energy? What is electrostatic potential energy? The electrostatic potential energy is defined as the amount of external work done. Say there were 2 point charges, right? So there was Q1 and there was Q2. This electrostatic potential energy means the amount of external work done, the amount of external work done in moving, say if this is a unit positive charge, moving a unit positive charge from a distance of infinity to a separation of r. So from a distance of infinity, so what is electrostatic potential energy? It's the amount of energy, it's the amount of external energy, or it's the amount of external work done in moving a unit positive charge from a distance of infinity to a separation of distance r. Now, the electrostatic force is conservative force. We had discussed this earlier. So I had explained this. So electrostatic force is conservative force, is a conservative force. Now, no Hari Prasad, we'll discuss that later, okay? The electrostatic force is conservative force. This means that the work done on a particle depends only on the initial and final positions. We had discussed this already. What do you mean by conservative force? The conservative force means if you see encounter any word called as conservative anytime, okay, if you encounter this word conservative anytime, it always means the work done depends only on initial and final position. The force applied or the work done depends only on the initial and final position of the particle and not the path followed. So electrostatic force. So what is the, guys, you have observed one thing. You have seen this electrostatic force and you have also seen electric force or electric potential. And so actually I've learned something called as electrostatic potential energy. And you have also seen something called as electric potential energy. What is there any difference between them? Guys, my question is there any difference between electric potential energy and electrostatic potential energy? Is there any difference? Yes, correct, Dhanush. To an extent, it is correct. Yes. So, what do you mean by electrostatic potential energy, and what do you mean by electric potential energy? Dhanush, your answer is correct. So electrostatic potential energy always deals with static. See, there is a word called as static. So it depends on, yes, uh, yes, yes, correct, Hari Prasad. Cool. Yep. Conservative force means that. But what do you mean by electrostatic potential energy? What is the difference between electrostatic potential energy and electric potential energy? What do you think the difference is? What is electrostatic potential energy? What is electric potential energy? So the only thing is, for electrostatic force or electrostatic potential energy, it's a time invariant, doesn't change with time, or it's always at rest. Static word, rest. Even the potential energy is at rest for electrostatic. When they define the term electrostatic potential energy, even it's for time invariant. It doesn't change with time. It means electrostatic potential energy means it doesn't change with time. Yes. And electric potential energy means, so whenever we define electric potential energy, it's a dynamic quantity. It changes with time. Okay, that's the only difference. Okay. So next we'll learn about potential energy. So we know that the external work done is given by W external is equals to Q1 Q2 by 4 pi epsilon naught into R. Right? So we have learned this. W external is Q1 Q2 by 4 pi epsilon naught into 1 by R2 minus 1 by R1. Now, what should we discuss? We should discuss about potential energy. What do you mean by potential energy? So For such conservative force, we can say that the work done is the change in potential energy. So we know the change in potential energy, I mean the external work done in moving this unit positive charge from infinity to a point is a conservative force. Now, for such conservative forces, we can write an expression that my work done, external work done, is equals to change in potential energy. So, how can we write this? The external work done, W external, can be written as change in potential energy. Say we know that the potential energy is denoted by U, capital U. Guys, you remember from your 11th, we represented potential energy with capital U. Okay. So the external work done for conservative force, it's always given as the change in potential energy. What is the change in potential energy? So when my charge was at infinity, when my charge was at infinity, it had, from with respect to origin, when my charge was at infinity, it had some potential energy. So similar to that of gravitational potential energy. Say in that case, when my body was at ground, when my body was touching the ground, its potential energy was zero. Okay, guys, please observe very carefully. When my body was touching the ground, in case of gravitational potential energy, yes, my potential energy was zero in case of gravitation. So I'll write G for gravitation. Now observe, when my charge is at infinity, guys, when my charge is at infinity, what happens to potential energy when, okay, here it is electrostatic. What happens to my potential energy when my charge is at infinity? Tell me this, guys. Is it maximum? Correct, Tejas. Correct, Danush. Awesome. Awesome, guys. So Prakash Gowda, I'm not okay. I discussed about gravitational potential energy. Let's come out of gravitational potential energy. My question is, guys, to whomever who didn't understand, I'm talking about electrostatic potential energy, or I'll take a time varying thing. So in electric potential energy, what do you think my potential energy is at infinity? What do you think my potential energy at infinity is? So two people have answered me already. Yes, Tejas correct, Danush correct, Prajwal correct. Oh, Jen, Mysore guys, awesome. All three are from Mysore. Awesome, guys. So others, please try to answer. So what happens? What do you think my gravitation? My electrostatic potential energy would be at infinity? Yes, correct. Nitya, correct. Correct, Nitya. So guys, see, as I explained here, my potential energy, when I do some external work for conservative force, the external work done is nothing but change in potential energy. Now, if the external work done is nothing but the potential energy, so if I apply this W external formula only for infinity, say if I consider my R1 is equals to infinity, what would I get? So consider I have only one charge. Yes, correct, Krish, correct, Bhargav, correct, Sayed. I'll call you Sayed. Yes. If my R1, if I have only R1, if I have only one charge, say if I have only, guys, come on, assume from origin, I have only one charge, that is Q, and this Q is at a distance of infinity. Okay. Now, if this is my distance R or R1, if I have to bring this charge, so what do you think the potential energy of this charge Q at infinity? What do you think the potential energy of this charge Q at infinity? What is the magnitude of potential charge of this Q at infinity? See, you know, okay, what is the force experienced by this charge at infinity? Say, okay, I'll consider two system, two charged particles, say q1 and q2. So have to, guys, let me put this way, have two charged particles q1 and q2. Now q1 is at origin and q2 is at infinity. What is the electrostatic force experienced by q2 because of q1? If you tell that, you'll get the answer. What is the potential energy? Correct, Tejas. Yes. I had already answered. I'm waiting for others to answer, guys. So others ದಯಮಾಡಿ ಆನ್ಸರ್ ಮಾಡಿ, ಟ್ರೈ ಮಾಡಿ. ಏನಾಗುತ್ತೆ? ಓಕೆ, ಎಕ್ಸ್ಕ್ಯೂಸ್ ಮಿ ಗೈಸ್, ಯೂಟ್ಯೂಬ್ ಪೀಪಲ್ ಪ್ಲೀಸ್ ಎಕ್ಸ್ಕ್ಯೂಸ್ ಮಿ ದಿಸ್ ವೇ, ಐಮ್ ಸ್ಪೀಕಿಂಗ್ ಕನ್ನಡ. ಸೊ ನೋಡ್ರಪ್ಪ, ಈಗ ನನ್ನ ಚಾರ್ಜ್ Q2 ಇದೆಯಲ್ಲ, ಅದು ಇನ್ಫಿನಿಟಿಲಿದೆ, Q1 ಒರಿಜಿನಲ್ ಇದೆ. ಸೊ Q1 ಇಂದ Q2ಗೆ ಇನ್ಫೈನೈಟ್ ಡಿಸ್ಟೆನ್ಸ್ ಇದೆ ಅಲ್ವಾ. ಇವಾಗ ಬಿಕಾಸ್ ಆಫ್ Q1 ವಾಟ್ ಇಸ್ ದ ಫೋರ್ಸ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಬೈ Q2 ಹೇಳಿ? ಕರೆಕ್ಟ್ ಅಲ್ವಾ? ಸೊ ಹೆಂಗೆ? ಎಫ್ ಇ ಈಸ್ ಈಕ್ವಲ್ಸ್ ಟು 1/4 pi, okay, I'll take it as k only, k q1 q2 by r square. If my r is equals to infinity, if my r itself is infinity, my fe will be equals to 0, right? If my r is infinity, my fe will be 0. Then what will be my electrostatic potential energy? What will be my u? What will be my u? So if I take this w external, u is equals to w external, then that is nothing but, say for, I'll multiply these two, q1 q2 by 4 pi epsilon naught into 1 by r1. I have this. So if my distance r1 is infinite, then what is my potential energy at infinite? Yes, correct Hari Prasad. Hope now you guys got that. So if my distance is infinite or at infinity, the potential energy experienced u of infinite will be equals to 0. How? If I substitute q1 q2 by 4 pi epsilon naught into r, if I substitute r as infinite, my potential energy at infinity will be equals to 0, because yes, correct Hari Prasad, cool. Yes, correct Hari Prasad. Yeah. So if r1 is equals to infinity, then u of infinity will be equals to 0. Now this point where I have 0 potential energy, this point will be considered as my reference point. Guys, this is very important point to note. So at infinity, my potential energy is 0. This point will be considered as my reference point for calculation of all potential energies. Make a note that, yes, at infinity, u of infinity is 0. So this point at infinite distance will be considered as my reference point for calculation of all potential energy at any given point. Okay, so we'll learn that. Now, then if that's the case, the potential energy expression is given by what? The potential energy expression is given by ur is equals to q1 q2 by 4 pi epsilon naught. When r1, see, I'm substituting only r1 as infinity, then I'll get w external will be equals to q1 q2 by 4 pi epsilon naught into r. So that will be my potential energy for any given point. So what I'm doing, I'm taking the reference point as infinite. At infinity, my potential energy will be 0. So with respect to this with respect to this point, if I calculate any other potential energy, I'll get its value. I'll get the magnitude of potential energy. Yes, guys. Hope you guys understood this. Artha agidya? Yes. So my potential energy, yeah, is for conservative forces. My potential energy or change in potential energy is nothing but the external work done. So what does this mean, guys? What does this mean? What does this statement mean? The change in potential energy will be my external work done. Say I had to move this q2 from a distance. Say I won't take infinity now. I'll take say some distance r2 to r1 or r1 to r2. Right now, say my infinity point is somewhere farther away. I'm going to give one more example. Say, if consider this condition, I have Q1, Q2, and an infinity point. Okay. Now, from infinity, if I have to bring, I have to apply more force. At infinity, there will be zero potential energy, but here I'll be having some potential energy. Now, how much work is to be done if I have to move this charge Q2 from distance of R1 to a distance of R2, if I consider this is R2. So the net amount of work done from in moving this Q2 to this position will be nothing but the change in its potential energy at those 2 points R1 and R2. Okay, that's what I meant in this. Hope this is understood, guys. Yes. Okay, everyone replied with yes. Cool. So, guys, one more thing. So, if there are two like charges, then the potential energy is always positive. Please remember, if there are two like charges, if Q1 and Q2 are two positive charges or two negative charges, then the potential energy is always positive. If Q1 and Q2 are unlike charges, then the potential energy is negative. Okay. Yes. Reply, guys. If my value of, if my charges Q1 and Q2 are positive in nature or like charges, both positive, both negative, then their potential energy will be positive. If Q1 is positive and Q2 is negative, then the potential is negative. This potential energy will be negative as if we bring R2 from, no, see, we are doing some external work done, right? We are doing some external work. So, Hari Prasad, I think yeah, as I mentioned earlier, when we are doing some external work, it's always considered positive. Okay. Its potential energy will be negative. No. Okay. Now, what happens if we have system of charges? Say, how do we calculate potential energy for system of charges? So we'll consider the first condition. So in a system, if there are only two charged particles, guys, tell me, in a system if there are only two charged particles, how do we calculate potential energy? How do we calculate that potential energy? So then the potential energy will be given as U is equals to U12. It's nothing but the force between them, per distance, that is given by Q1 Q2 by 4 pi epsilon naught into R12. Okay, then the potential energy is Q1 Q2 by 4 pi epsilon naught into R12. Okay, similarly, if I have a system of three charged particles, what would happen? How do I calculate my potential energy? How do I calculate my potential energy in this case? Guys, you guys have solved this many times already by now. Yes? Yes, correct. Superposition principle. Correct, Dikshita. So if I have system of three charged particles, then their potential energy is given by U is equals to U12 plus U13 plus U23. Yes, correct. As we calculated. Yeah, correct. Then U net is equals to Q1 Q2 by 4 pi epsilon naught R1 plus, yes, by applying principle of superposition. So this is how we calculate the potential energy for system of charges. Okay. Next, we are going to discuss about electric potential. So here we will be learning about charges. So what happens to the electric potential, and when we have a point charge, what happens and stuff. So guys, we'll keep that for tomorrow. For next class. Please try to revise all your basic concepts till then. and try to yeah, try to learn those. So guys, apart this, I'll be posting another DPP today. So it will be having other 10 questions on electrostatics part 1. So there will be another set of 10 questions in electrostatics part 1, guys. So I hope everyone is solving it. Is there any doubts so far in those questions which you have solved? Is there any doubts in the questions which you have solved so far? Okay, no doubts. So how many solved all 10 questions? I don't know if you guys were able to solve all 10 questions. Did anyone solve all 10 questions so far? Okay, guys, cool, chill. So if anyone requires any solution, handwritten solution, or anyone wants me to discuss any question in particular, please let me know. Yes, Anusha. Can I know the question number? Anusha, yes. You said you had a doubt. Can I know the question number? First question. Acha. So, okay. I'll try to check out what's the question. What was the question? Okay, so I don't know. I'm unable to access. I'm unable to come out of this platform right now, Anusha. I'll discuss you that question. Please, can you give me that question if you have like, if you have already. I mean, what was the question on? Can I know, please, so that I can discuss that here? Yes. So the question was, I'm trying to search that. Have posted it in your WhatsApp group, right? Please, guys, give me some 2 minutes of time. I'll search that question and let you know. So, batch. Why? Where is that? Okay, so so I don't know why I'm unable to find those document anywhere. So if you, it would be great if you guys could let me know what the question was. Hi Anusha. So any other doubts? So please keep me post. Like I'll take this question. Anusha, you are in Mysore. Okay, I'll post all the answers if you require, guys. So I'll post the answers in your WhatsApp groups and Telegram groups from the DPP. So I will be sharing you one more document, that is the pre-reading document for you guys for next class. So I'll be sharing that, and one DPP of 10 questions. So it will be of 3 different levels for one for 5 questions for NEET and 5 questions for JEE. So it's the previous year question papers and also the standard questions which I'm going to share today. Okay, please try to solve and we'll meet again in Monday. Okay, guys, then see you again on Monday. Then bye.